Section: Introduction. In this section, we discuss the introduction of our paper. During the pre-training phase, large language models, LLMs, gain various abilities, some of which can be harmful if misused, such as aiding in cyber attacks or creating bioweapons. Recognizing these risks, the Executive Order on Artificial Intelligence stresses the need for responsible AI development. To mitigate these dangers, LLMs are generally trained to avoid engaging in harmful activities. However, this refusal can be bypassed through techniques known as jailbreaks and other attacks. We can tackle these vulnerabilities by ensuring that harmful knowledge is not embedded in the model's weights. Unfortunately, filtering out such knowledge from the vast pre-training datasets and retraining the models is not practical. We propose using machine unlearning to eliminate harmful knowledge from models, which offers better safety than mere refusal. However, most evaluations of unlearning methods focus on outputs rather than confirming if the knowledge has been removed from the model's weights. Previous studies have shown that even after applying unlearning techniques, harmful information can still be retrieved through various methods, including altering the question format. Even with advanced unlearning methods like RMU, harmful information can still be accessed via jailbreaks. To create effective unlearning methods, we need robust evaluation frameworks to guide our research. Our contributions include a framework for assessing how well unlearning methods remove knowledge from model weights. We develop new datasets and adapt existing ones to meet our framework's criteria. Using this framework, we quantify the hidden knowledge that remains in the model weights after unlearning. We evaluate common unlearning methods, such as gradient ascent, RMU, and training on incorrect facts. Our findings reveal that after our attack to recover hidden information, we can retrieve at least 88% of the pre-unlearning accuracy across all evaluated methods, provided that the unlearning maintains good performance on tasks that were not targeted for unlearning. We also explore related work on refusal in LLMs, noting that while reinforcement learning with human feedback, RLHF, aims to reduce harmful behaviors, it does not fully protect against jailbreaks or other attacks. Various unlearning methods have been proposed to address the limitations of RLHF, including gradient ascent, which alters the training process to increase the loss for information we want to unlearn, and RMU, which modifies model activations for harmful prompts while keeping them intact for non-harmful ones. Previous evaluations of unlearning have often relied on task performance or output similarity, which do not effectively capture hidden knowledge. Some researchers have suggested metrics to better assess unlearning effectiveness, such as testing on more challenging cases and using membership inference attacks, MIA. However, evaluating jailbreak robustness remains complex, as some attacks may succeed while others fail. In terms of white box evaluations, methods like linear probes and relearning time have been introduced. While linear probes can reveal information in activations, they may not detect knowledge in weights effectively. Relearning time measures how quickly a model can regain accuracy on unlearned knowledge, but this metric is only meaningful when compared to models that were never trained on that knowledge, which is difficult to establish due to the high costs of LLM pre-training. Section Summary. In this section, we discuss the challenges and vulnerabilities associated with large language models, LLMs, in terms of unlearning harmful knowledge, highlighting that current methods often fail to completely remove dangerous information from model weights. We propose a new evaluation framework to better assess the effectiveness of unlearning techniques, demonstrating that even state-of-the-art methods can still allow for the recovery of harmful knowledge. Section: Unlearning as removing information from the weights. In this section, we discuss unlearning as a method for removing information from model weights. We note that while unlearning can mean making information harder to access, true removal of information is a stronger assurance. We aim to evaluate how effectively an unlearning technique eliminates specific information. For instance, if we unlearn information about a question, such as the founding year of the World Health Organization, the model's weights should not change predictably if the answer is altered. We define a situation where the answer to a question is represented as a random variable. An unlearning process is considered successful if the mutual information between the modified weights and the answer is zero, meaning no information about the question remains. We focus on questions that are difficult to guess, rather than those that can be inferred from general knowledge. To assess the presence of information in the weights, we propose a new adversarial approach. We identify independent facts that should be removed from the model after unlearning. These facts are divided into training and validation sets. An attacker attempts to recover the validation facts using the model weights and the training facts. If the unlearning is effective, the attacker should not be able to recover the validation facts from either source alone. Any successful recovery indicates that the information was hidden, not removed. We seek to find an optimal unlearning technique that minimizes the accuracy of the attacker on the validation set. The specific attack we analyze is called retraining on training facts, RTT, where the attacker retrains the model using the training facts. By measuring accuracy on the validation set after this attack, we can infer the mutual information. High accuracy suggests high mutual information, while accuracy close to random chance indicates low mutual information. We also explore how training on the training facts might inadvertently reveal hidden information. If unlearning makes information harder to access, RTT should still make the training facts easier to access, which could also affect the validation facts. We will examine the reliability of this transfer in a later section. For our metric to be effective, the training and validation sets must have minimal shared information, ensuring that training on one does not improve accuracy on the other. Section Summary. In this section, we discuss the concept of unlearning as a process that effectively removes specific information from model weights, rather than just making it harder to access. We introduce a method to evaluate unlearning effectiveness by measuring an attacker's ability to recover independent facts from the model, aiming to minimize the accuracy of such recovery to ensure that the information has been truly removed. Section: Experimental Setup. In this section, we outline our experimental setup. To conduct our evaluations, we create datasets that meet specific criteria, which we then use for unlearning and retraining. Our evaluations can also be applied to models that have already undergone unlearning. For our datasets, we aim for certain properties. We want minimal shared information among facts, meaning that learning one fact shouldn't aid in learning others unless that information is already in the model's weights. We also ensure that models perform well on the dataset before unlearning, so we don't need to fine-tune them, which could affect unlearning outcomes. Additionally, the data should reflect real-world scenarios where unlearning is applicable. We develop several datasets, each varying in how well they meet these criteria, and we also create retained datasets to ensure that the model retains important capabilities. We have a dataset of significant 20th century events and their corresponding years, which we split into 5 parts, using 4 for training and 1 for validation. For the retained dataset, we utilize Fine Web Edu. For the MMLU dataset, which has 58 subsets, we categorize them into 10 groups with minimal shared information. We use 4 categories for training, 1 for validation, and the remaining 5 as the retained dataset. WMDP deduped is a filtered version of WMDP that reduces overlap among questions. We split it into 5 parts, using 4 for training and 1 for validation, with Fine Web Edu as the retained dataset. The Random Birthdays dataset consists of randomly generated names and birth years. Since it's randomly created, we first fine-tune the models on this dataset. We again use 4 splits for training and 1 for validation, with a subset of MMLU categories for the retained dataset. This dataset helps us test unlearning methods when we are confident that the facts are independent, and we verify this independence, with results provided in the appendix. For each dataset, we use both plain text and multiple-choice question formats. Since unlearning should apply to facts rather than specific formats, we perform unlearning using the plain text format and conduct RTT and evaluation with the multiple-choice format. The plain text format is generated from the multiple-choice format using GPT-4o, and we provide examples in the appendix. We also illustrate how the format affects unlearning performance. In our experiments, we primarily use Llama 3, 8B, but we observe similar results with other models. We apply the plain text format for unlearning. The main unlearning methods we test include gradient difference, which involves adjusting the model's gradients based on forget and retain datasets, and RMU, which modifies activations for harmful prompts while keeping them intact for non-harmful ones. We also use random incorrect answer, where we create plain text data points for each incorrect choice and apply gradient descent. Unlearning is effective only if the model maintains performance on other tasks. Therefore, we adjust the unlearning strength for each method to balance low forget accuracy with high retain accuracy. We consider results where the drop in retain accuracy is no more than 5% compared to the original model, along with additional results in the appendix. For retraining and evaluation, we use the multiple choice format. We experiment with various learning rates and run RTT with 2 random validation splits. In each run, we fine-tune the model on the remaining 4 splits and report the average accuracy across runs, selecting the learning rate that yields the highest validation accuracy. Each split contains 157 data points, with 4 splits for training and 1 for validation, totaling 628 data points for training. We maintain consistent RTT hyperparameters across all datasets and unlearning methods, with details and uncertainty estimations available in the appendix. We also explore different loss options and discuss the results in the appendix. Section Summary. In this section, we describe our experimental setup, which involves creating various datasets with specific properties for evaluating unlearning and retraining techniques. We utilize models like Llama 3 for unlearning experiments, employing methods such as gradient difference and RMU, while ensuring that the model retains performance on non-unlearned tasks through careful configuration of hyperparameters. Section Results. In this section, we observe that both RMU and GD effectively decrease accuracy after unlearning, while RIA shows a smaller reduction in accuracy. For all methods, RTT manages to restore the accuracy on the forgotten data to a level close to the original, indicating that most information was hidden rather than completely removed from the model's weights. To measure how well an unlearning technique removes information, we calculate the recovery rate, which is the accuracy of the unlearned model after RTT divided by the accuracy of the original model after RTT. A lower recovery rate indicates better information removal. Our tests reveal that all recovery rates exceeded 88%, suggesting that the information removal was not very effective. We also investigate whether the retain loss limits the unlearning method's ability to remove information from the weights. Our experiments show that even with significant losses in retain accuracy, RTT can still recover accuracy on the forgotten dataset. Notably, RTT often recovers accuracy even without a retain loss, suggesting that unlearning methods are not hindered by the need to maintain performance on the retained dataset. Next, we examine how the format of the text used for unlearning impacts performance. Our findings indicate that using plain text generated by GPT-4o yields the best overall performance across various unlearning methods and is applicable to all MCQ datasets. RMU outperforms GD when the unlearning dataset is related but does not necessarily share the same facts as those used in RTT and evaluation. Conversely, GD excels when all datasets use the MCQ format and the loss is limited to answer tokens, implying that RMU may generalize unlearning better than GD. We also explore high granularity knowledge hiding, where models can conceal facts at different levels. For instance, a model might hide all birthdays, low granularity, or only specific individuals' birthdays, high granularity. RTT aims to eliminate the general tendency to hide facts, potentially succeeding only when information is hidden at a low granularity. To test RTT under high granularity, we create a model that hides knowledge at this level using a random birthdays dataset. We fine-tune the model to achieve high accuracy while manipulating the layers to ensure knowledge remains hidden. Using a retained dataset from the same distribution as the forget dataset, we push the model to develop a high-granularity hiding strategy. We perform unlearning with GD and various hyperparameters, achieving 32% forget accuracy and 72% retain accuracy. After applying RTT, we successfully recover the forget accuracy to 92%. This suggests that RTT can retrieve hidden knowledge even with high granularity, although the transferability of these results to more natural examples remains uncertain. We also compare RTT against techniques designed to complicate fine-tuning on specific information and find that RTT can effectively recover information. However, we note that RTT is resource-intensive compared to simple accuracy evaluations, as it requires fine-tuning and hyperparameter searches. Additionally, RTT does not guarantee that information is entirely removed from the weights. It simply raises the standard for evaluating unlearning methods. If an unlearning technique hides information across different parts of the model, RTT may not recover accuracy even if the information is still present. Nonetheless, RTT performs well for current unlearning methods, as we demonstrate in the appendix. Section Summary. In this section, we demonstrate that while RMU and GD effectively reduce accuracy after unlearning, RIA shows less impact, and RTT can recover accuracy, indicating that information is often hidden rather than removed. We also find that RTT performs well even under high granularity knowledge hiding, although it does not guarantee complete information removal from the model's weights. Section. Low leakage datasets are hard to build. In this section, we discuss the challenges of creating low leakage datasets. Our evaluation relies on a set of facts that exhibit low leakage, which may not always be achievable depending on the unlearning objectives. This limitation means our evaluation does not assess the effectiveness of unlearning capabilities. For instance, if we aim to unlearn coding skills, it becomes difficult to construct training and validation sets with low leakage. We note that simply removing information is a stronger requirement than what might be necessary. Ensuring safety could involve making information difficult to access rather than completely removing it. For example, we could achieve jailbreak robustness without altering the model weights, but assessing this robustness directly is challenging, often leading to inflated estimates. We propose an alternative approach that may offer better safety guarantees, though future research might identify less conservative targets that still provide adequate protection. Based on our findings and inspired by previous work, we recommend the following for future research on mitigating dangerous capabilities and knowledge in AI models. Clearly state whether the method aims to remove information or just make it harder to access. When the goal is to eliminate capabilities or knowledge, we should evaluate the method against attacks designed to recover that information, such as the RTT attack we presented. Additionally, we should release the models and code used in our methods to enable other researchers to assess the robustness of our approach.